Hey, team! Chemistry Coach coming at you for a new journey into the realm of gases. We're going to be looking at gases, liquids, and solids, but we're going to keep liquids and solids for second semester typically. Not depends on the book, the class you take, but gases are a heck of a lot easier because some of the assumptions we're going to make to mathematically model. Liquids and solids, not quite so easy. All right, so we'll do a journey just for gases, and then we'll worry about liquids and solids later down the road. All right. So I'm going to kind of twist it up a little bit. A lot of times when you're taught gases, they start with experimental observations. Hey, we notice this behavior. You come up, you're probably aware of the gas laws and P equals nRT and all this, Boyle's law and Charles' law, all that fun stuff. And that's typically how I teach it in introductory chemistry. And then we look at that, experimental behavior and then try to model that behavior. I'm going to kind of twist it on its end here, and we'll start with the models in the theory that tries to explain gas behavior. And then when I introduce the gas laws later in different videos, we can look back on it and go, oh, can make that connection there. So we're not just going to twist it up. Really doesn't matter which way you do it. We're going to get through all this stuff either way, but I want you thinking about gases and chemistry in general at the molecular or atomic level. So there's a particular way I want you to picture gases, and then we'll look at that behavior and try to expand that to a macroscopic situation that we can see and study in the laboratory. All right, so anyway, kinetic molecular theory, or KMT, was the models put together mostly by Maxwell and Boltzmann. You'll hear those names over and over and over and over and over in physics and chemistry. Again, in the mid 1800s, this isn't something that happened, in one eureka moment. This took quite a bit of statistical mathematics to study, but it's amazing what they could do back then. I mean, don't think computers were invented in the mid 1800s. To do the stuff they did is amazing. Smart people, right? That's why they're immortalized in science, both physics and chemistry. But they put this together to try to model experimental behavior of gases. So they put together a series of postulates, kind of like Dalton's atomic theory, a bunch of postulates of what an atom is and trying to explain certain laws and behaviors. Exact same idea. So we will list a few of these postulates one at a time. I'm not going to go into the gory mathematics of how a lot of these equations were derived. If you're interested in the physics and statistics derivations of this stuff, go for it. Read into it. I'm just going to kind of give you the snapshot, right? We're taking a tour through a country, get off the bus, take some pictures. Boop, boop, that was it. Hey, get back on the bus. All right. If you really want to dig into the gory math, go for it. But let's start by putting some, and some of them are just concepts. Some of them are I'm going to give you the results of some pretty sticky calculations. All right. Postulate number one, and there's no specific order you have to go in. You might take a class somewhere else, and my postulate 2 is their postulate 3, or they combine postulate 2 and 3 into postulate 1. Whatever, we're just going to get the concepts across to you, right? The first concept about gases is a gas, like inside a balloon or some container or something like that. We can't see it with our eyeballs, especially individual particles. But we picture it as a collection of tiny, tiny little particles, and they're going to be, probably neutral atoms or molecules. You could have like argon atoms or neon atoms, like a neon gas tube, or carbon dioxide. You breathe into a balloon, you got some water particles, some carbon dioxide particles. Heaven knows what you had, at the birthday party. A little burp, what comes out of there. But it doesn't matter. We're just going to treat them as little tiny particles. And they're constantly, they don't just sit there and do nothing. They're constantly moving in random motion. Once it goes in there, it's boop, 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 boop. It's like when you play pool or billiards, you go crack, and the cue ball hits the balls, and the balls are flying. Imagine they just keep going forever. And that's only in 2 dimensions. Imagine that in 3 dimensions. So here's like a 2-dimensional slice of a box of some container, and these little particles, and they could all be the same particles, different particles, doesn't matter. They're so tiny. And they're moving around, and they can do one of 3 things. Move around without hitting something, right? But eventually they're going to strike something, right? They're in a closed container. It's like you're in a crowd, just walking around. You're either going to, if you just walk in a straight line, a bunch of zombies just walk in a straight line, you're either going to hit a wall or another zombie. You know what I mean? Horrible analogy, but I'm a zombie apocalypse kind of guy. So a particle can, boom, hit and have a collision with the surface of the container. We're going to talk about the impact, no pun intended, of that later. And it just bounces off, right? Changes direction. We'll talk about the fact that it can transfer energy in that process too. Or particles could, boom, hit each other, whether they're the same or different, doesn't matter. So here we have two different particles that go bang, smack into each other, bounce off like two, billiard balls, a cue ball hitting, like an 8-ball, bam! They bounce off in different directions. We'll see there's a transfer of energy there, changing direction. So we can have a collision between particles or a collision with the surface. So that's essentially all a gas is. It's a collection of tiny particles moving in constant random motion, and they'll collide into either the surface of the container or each other. Over and over and over and over and over. They ain't gonna stop. So just one quick definition, not critical at this point, but mean free path is kind of the average distance a particle is going to travel until it hits something, right? So it may be longer here, shorter there, but on average, how far is a particle going to travel until it has a collision with something else, right? Pretty simple definitions. I like that. Let's look at the consequence of this. Already giving you some hints. Hopefully postulate number 2, even though I skipped a lot of mathematics, makes gut sense to you. I think if you took a physics class, I'll kind of look at it from a physics point of view and from a kinetic molecular theory point of view. And Ixnay, magic fairy dust, poof, 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 this equation occurs. If you want to see the derivation, you can read some kind of textbook or something like that. But in general, would it make sense if a particle is moving and hits the inside surface of the container wall, bounces off, that creates pressure. That's essentially what pressure is. It's the particle going bam. It shouldn't hit so hard. Right? I think, does that make gut sense with you? You're like, okay, that's pressure. Okay, well, let's look at it from a different point of view, right? Probably from physics, you're familiar with force divided by area, right? So force, how hard is that particle hitting? What's the force? Boom! We're going to look at pressure specifically, units and things like that in another video when we look at properties of gases. But you see pressure, the harder it hits, the more force it has, the greater that pressure is going to be. Now remember, if you're dividing by area, so the smaller the area, the more pressure there's going to be. It's kind of like, if you're dancing with someone and they step on your toes, but they have, cowboy boots on or galoshes or something or tennis shoes, it doesn't hurt so much. But if they got stiletto heels on, oh, right? That's why swords have little pointy ends, bloink, right? Because that's a really tiny surface area with a lot of force, right? Versus poking somebody with a big stick with a big end, it just bounces right off, right? You get the difference. Okay, force over unit area. Pretty simple. Increase. And I want you to think about ways, how could we impact the pressure? We're going to look at this when we look at gas laws later. What happens if we alter this, parameter of a gas? What if we change the temperature of the gas? What if we change the volume of the gas, right? What if we change the number of particles? How would that impact different parameters, like the pressure, for example, right? Well, I want you to think about it from a kinetic molecular theory point of view on a molecular level or atomic level. How could we increase it? Well, if you increase the force that particle strikes, you increase the pressure. And if you decrease the area, which is pretty hard to do, right? So that's not very useful for us at this point. But kinetic molecular theory looks at force as, okay, we have a collision. So there's this term they use called impulse. Impulse power. Don't think about, little shows where you're going through space and right? Go to impulse power. But impulse, think of impulse as, would you agree, if that particle strikes, boom, there's a momentum transfer, right? Boom, and it bounces off. So there's a momentum transfer to the surface, okay? And then it bounces off and goes somewhere else. So that momentum transfer due to the collision with the surface, we're going to call impulse, all right? Would you agree that the more particles there are, or the more often they hit, that would increase the amount of pressure, right? So boom. So we call that the collision frequency. So that's going to be a huge term later when we think about how can we change the pressure. Well, we can really impact the collision frequency, right? Well, if I increase the temperature, it's moving faster. Oh, all right. It's moving faster, so it increases the impulse, and it's hitting more often. If it's traveling faster, it's going to hit more often. It's like the zombies walking versus running, right? They're going to bounce off the walls more if they're running around. Or if you have more particles, more zombies, more collisions. Oh, all right. Again, my horrible zombie apocalypse example, a bunch of zombies in a box, moving around. So you can kind of, it's easier to think of it, I think, as a chemist from a kinetic and molecular point of view, collision frequency times impulse. Right now, so I'm sure collision frequency is probably, how often the particles are striking. Impulse is probably something new, but I think it makes sense. Oh, it's that momentum transfer after it hits. If you plug in the mathematical equations, skip, magic fairy dust, poof, 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 you end up deriving this equation for pressure from kinetic molecular theory. So 1/3, don't worry about that number. It comes from X direction, Y direction, Z direction, all this kind of stuff, because we're moving in three dimensions. N is the number of particles. Makes sense. Impacts the collision frequency. Volume, right? Impacts the collision frequency. We can see the dependency of the pressure on the volume. Oh, that's going to be a law later on down the road. M, the mass, right? This deals with the impulse, the momentum transfer. And then this is called the mean square speed. We're going to really look at that later on when we look at the distribution of speeds of gases. We're going to find out that they're not all moving the same speed, because when they collide with each other, right, there's going to be a transfer of kinetic energy and a change in speeds. So that's the mean square speed, or you take the mean of that. So that's another way of looking. And in my class, I'm not going to make you calculate things with either of these equations. I just want you to think about it in terms of collision frequency times impulse, or force over unit area. Probably easier with this one. Right? Get those terms down. Let's move to the next postulate. This next one, sometimes I'll put a star next to it. Oh, that's not postulate number 2. We already did postulate number 2. This is postulate number 3. Gotta number things properly, right? We're going to make an assumption here. No, we don't have to make this assumption, but to make our lives much less miserable mathematically, we're going to make this assumption. And this is going to lead to what we call an ideal gas versus a real gas, okay? I'll put a star next to this. Is this going to come back and bite us in the tushy later? We are going to make the assumption that the volume of the actual gas particles, the little particles moving around, collectively is so tiny. How tiny is it? It's so tiny compared to the volume of the container, it's effectively 0. Which means we can just use the volume of the container. We don't have to subtract out the volume of the gas particles. That's going to be a pain in the butt. We're going to do later when we deal with real gases. But for now, we're just going to make the assumption, because these particles are so, atoms and molecules are so itsy bitsy, I can collect them all. Right? I can take all the particles in this room, put them in the palm of my hand. I still can't see it. Compared to the volume of this room I'm in, the volume of those particles is irrelevant. Right? It's like I can take a little walk over to the Pacific Ocean. Pacific Ocean, California. Oh, I gotta get my geography right. I could go take a stroll over to Balboa or San Clemente. I used to live in San Clemente. Go over to the beach over there. I could take a spoon. I could scoop a spoon of water out of the Pacific Ocean and go, I have decreased the volume of the Pacific Ocean. All right. Technically, yes, but the ocean didn't notice, because the ocean's pretty big. See what I'm saying? It's the same idea. I mean, it's kind of silly to think about that. Yes, I decreased. Okay, statistically, yes, you did. I don't know how many decimal places. But the volume of the particles is just irrelevant to the volume of the container itself. So are you okay? Not that you have a choice. We're going to assume that the volume of the particles is squatoli 0. We're going to have to correct for that. Actually, later on down the road, that'll be the last video for this chapter, because it's not fun at all. I hit pause because accidentally I wanted to show you the difference. Here's the container. You ready? Ready? Here's the particle. You ready? Watch this. Did you get that? Did you get that? The volume of the particle compared to the volume of the container. Yeah, don't worry about it. All right, my postulate number 4, which may be someone else's postulate number 3 or 2 or 1, whatever. We're also going to make another assumption, right? It's going to really simplify our mathematics again and create what's called an ideal gas. Looking at postulates 3 and 4 gives us an ideal gas. we're going to make an assumption that as particles are moving, right? So say this green particle's moving this direction, the blue particle's moving this direction. We're going to assume that they don't even recognize each other, that the forces between the gas particles are just irrelevant. They're negligible unless they actually strike each other. In reality, not necessarily true. So to account for that, it's going to complicate the mathematics quite a bit. That would be a real gas. But for example, they just pass right by each other, like two people walking down a sidewalk. They don't even know. I can't look in your eyes. I'm the type of guy. I'll look in the eyes and say, "Hey, what's up?" I'll look at your eyes until you look at me. Are you looking at me? You're looking at me. Oh, hi. But a lot of people never even look at me. I'm like, I just want to say hi. I just want to say hi. Say hello. How's your day? I'm just looking at, but I'm not going to say it unless they look at me first, right? It's kind of weird. But a majority of people don't even look at me. I'm like, oh my gosh, I just want to say hi. My wife hates it. I'll go in an elevator and actually turn around. Hey, what's up? She's like, don't talk to people in the elevator. Oh, why? I don't understand. But anyway, that's just me. So we're going to assume zero interaction between them. If they hit each other, there's a transfer of energy and blah, blah, blah. Speeds can change. That'll be the next postulate, by the way. In reality, though, it's possible if there's a slight attractive force, these could be coming at each other and then they don't hit, but this is traveling this way. Maybe this is a little attracted and it goes, woo, and it changes its pathway. And it would have collided with the wall if we didn't assume there's attraction, but if we do assume attraction, maybe it doesn't collide with the wall at the point in time it normally would have if there wasn't an attractive force. See, it could change the pathway a little bit. So anyway, really simplifies the mathematics. So I'm going to write this down. If we take postulate 3 and postulate 4, right? So postulate 3, postulate number 3, I'll put postulates, and number 4, assumptions, right? Assuming the particle volumes are collectively zero compared to the container, and then no forces of attraction or repulsion between the particles, which isn't necessarily true in real life. But if we account for those, give us ideal gases. So you probably heard of the ideal gas law. We're going to get to that. We're going to get to the PV equals nRT. I call it the perfect equation, but PV equals nRT. That's assuming ideal gas behavior where the particle volumes are zero compared to the container and there's no interactive forces between them. But if we account for those, we're going to get what's called a real gas, which is there's a modification for these two factors in postulates 3 and 4. So it won't be that nice simple PV equals nRT anymore. It'll be this ugly mess. All right, let's get to our last postulate. All right, this last postulate's probably one of my favorite. I just love this kind of stuff, right? Energy stuff. So if we have a gas sample at a constant temperature, its total energy will be constant. But because of the motion of the particles, right, they can collide with each other. So would you agree that when they collide, just like two billiard balls collide, a faster one may slow down, one that wasn't moving, starts moving. There's a distribution of kinetic energy upon collision. So collisions between gas particles, right, allow for kinetic energy transfer between the particles. So some can gain energy, some can lose energy. That results in a distribution of kinetic energies of gas particles. So the individual, but you pick one, I'll take that goldfish right there, Daddy. And you're like, there's 300 of them. You're like, oh, that particle right there, what's its kinetic energy? It's changing. Every time it collides with another particle, bing, 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 bang, bang, bang. Remember the mean free path? Boop, 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 boop. It can lose or gain kinetic energy upon collision. So it's speeding up, it's slowing down, gaining energy, losing energy, yada, yada, yada. Like if these two hit, and then recoil off each other, let's say this one imparts some kinetic energy to this one. So this one's kinetic energy goes up, this one goes down. So I could take 100 particles, start them all at exactly the same kinetic energy and have them not moving magically. Snap my fingers and say go at some temperature. Got a total energy that's constant, but when I say go, collisions occur almost instantly. Some get more energy, some get less energy, blah, blah, blah. But the majority will still have relatively about the same kinetic energy, be like an average value, but it'll spread out, and there'll be a few. There might be one where it hits this particle and gains some, and hits that one and gains some, hits that one and gains some, and hits that one. There could be a just weird particle with a really, really, probably to your right, a really, really high kinetic energy. It's like this weird outlier. And you have one that's like, every time I collide, I lose energy. Oh, I lost energy again. I lost more energy. I lost more energy. And it gets to the low end, but you don't have too many at the extreme ends, so you get this like a bell curve sort of like distribution of energies at the end. We're going to analyze that bell curve pretty hard later on when we look at the distribution of gas particle speeds. We're going to analyze that and look at the different kinds of averages we could have. But would you agree that we couldn't get the energy of any particular particle, but we could get the average? So we tend to use average energies in chemistry. So let me show you a couple equations, one from physics you've probably seen, and one derived from kinetic molecular theory on the average kinetic energy of a gas sample. Be right back. Here we go. Let's look at this distribution, right? It's just a very oversimplified graph. We're going to find out when we do molecular speeds later, it's not quite symmetric. Kind of leans heavier towards the higher end. But you tend to see a distribution that happens with the statistical distributions of just about, I mean, not everything, but a lot of stuff. Grades, average heights of people, so you get this distribution. And most people are around this height, but there's some really tall people and some really short people. Yippee! Weights. You got most people around here. You got some really heavy people, some really light people. You see a distribution, but we can calculate an average. So we tend to usually talk in life about averages. Most people do. What's the average height? This. What's the average mass? Blah, blah, blah. But that's for large groups of people or large, data distributions, lots of data points. But if you just pick one of those data points, like just one person, they could be, 7'3", shackish. They could be, 4'11", like some of my daughters, that kind of stuff. They're still growing, but don't have much further to go. You can't pick out one person. And just like a gas particle out of a collection of, say hundreds of trillions, you can't just pick out one and go, oh, we just look at an average, right? So here we go. And you'll have some that are pretty low in energy, some that are pretty high, but on average, they're going to be right around there. So we talk in terms of the energy of a gas sample as the average kinetic energy. We good? Good with that? So from physics, you're probably familiar with the average kinetic energy being 1/2 mass times volume squared, right? But a chemist doesn't quite look at it that way. Magic fairy dust from kinetic molecular theory. Thank you, Maxwell. Thank you, Boltzmann. Poof, 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 poof. This equation appears. You want to see where this comes from? You can read textbooks. All right. And again, we're not going to be dealing with these equations very often, at least in my class. We're going to look at it more qualitatively. But the average kinetic energy from a kinetic molecular theory point of view is 3/2 times RT over N sub A. What does that mean? Well, we're familiar with temperature, but that has to be the Kelvin temperature because that's the absolute temperature scale. It can't be negative. What if you're using the Celsius or Fahrenheit scale? You could have negative values and you'd have a negative kinetic energy. What does that mean? It doesn't mean anything, right? In Kelvin temperature, I guess technically you could go to 0. If you had a 0 Kelvin temperature, you'd have no kinetic energy because it's not moving. Right? Absolute zero temperature means lack of motion, which means it's sitting there. I don't think we've ever really even achieved that. We got close. We got pretty cold, but no, not going to happen. Right? N sub A is just Avogadro's number, relates to the number of particles. And R is a gas constant that derives from a bunch of other constants coming in there. So universal gas constant. There's 2 different ways we're going to look at it depending on the unit. So we'll see one that instead of joules has liters times atmospheres or liters times bars, depending on which rules you're looking at, which book. But when you're dealing with energy units of J, which is joules, R will be 8.3145 joules per mole Kelvin. And you'll see how the units cancel out if you do these types of calculations. So again, magic fairy dust. I'm not going to take 20 minutes deriving these equations for you. The one we did for pressure, and I think in postulate number 2, and then the one for average kinetic energy. But you can see now, take a look, and you see if this is a constant and that's a constant, and these are constants, the only variable is the Kelvin temperature, right? So kinetic energy is directly proportional to the temperature. So would you agree if we increase the temperature, this whole curve shifts over, right? It keeps its shape, but it shifts. The kinetic energy average shifts over because the whole curve shifts over this way. So if we did a higher temperature, that would be a higher temperature. Now it's gonna broaden out. It's gonna lower and broaden out. Same number of particles. It's just at higher temperature, there's more available kinetic energies. It's like being in a room and only having one door versus 5 doors, right? If I have 5 doors, there's lots of options. But if there's just one door, everybody's packing in there, right? So there are just, as you move to higher temperature, there's more possible kinetic energies. So you're gonna have fewer particles per individual kinetic energy. That makes sense? So as you move over, the graphs get lower and more spread out. They get squatter as you move to higher temperatures. All right, pretty straightforward. But does it make sense that the average would be higher if the temperature goes up? The average kinetic energy goes up. Yay! We're going to look at that in a lot more detail when we look at molecular speed distributions. But that's the essence of kinetic molecular theory. And what we're going to do is when I start introducing the different experimental behaviors of gases through the gas laws, we'll be able to look at it from a macroscopic point of view. Here's what we see in lab, and then think about it qualitatively from kinetic molecular theory and go, that makes sense, because if we increase the temperature, we increase the kinetic energy, which increases the speed, which increases the collision theory, which increases the pressure. Oh, see how that works out? We're going to have fun with this, gang.